Hello everyone. I'm Gonzalo. I'm a PhD student of microcosmos and part of the University of Strathclyde. I'm here to present the paper we made of deep reinforcement learning for plan execution. Now, this idea comes from we're trying to solve a problem that comes from satellites, where we have a satellite that is going around the Earth, and we lost communication for a period of time until it gets into a window of a ground station again. Now, during that period, it had to be autonomous and take all the actions, but the space is a really uncertain and non-deterministic environment where anything can happen, really. So what we want to do is we want to have a plan that is done by engineers and has some abstract assumption that are not introduced into the model and be executed as and just have some kind of agent that follows that plan as near as possible. Now, this non-deterministic and uncertain environment makes the engineers have to plan and make a highly conservative and robust plan so it can be executed. Now, the conservative plan does not maximize the potential reward due to taking actions in a really conservative way. Now, to solve this, we introduce a reinforcement learning agent as to execute that plan. Now, why do we use reinforcement learning? Well, replanning can be really consuming both in time and resources, while an agent that is trained by a reinforcement learning agent, so a reinforcement learning agent that's already trained, is really fast and can and is really flexible. Now, also, the reinforcement learning agent can choose any action in the action space, while other execution methods do not use as only a subset of the action space. So this possibility of choosing any action in the action space also gives it to the ability, if needed, to go completely off plan to sort obstacles, or in some way it could take advantage of opportunities. Now, we have defined that the action space is the same one as the one used in the planner. So now we need to define both the reward and the states that go into the agent. And this is first we need to define the reward. Now, the problem on defining the reward, and the question that popped up while doing investigating what it is what does it mean to follow a plan? Now, this might seem like a dumb or easy question, but we found out it's not. Now, let's have this plan. Let's state a plan. For example, it could be, let's go cooking, and you're going to make something. Now, you're making some type of soup with chicken. Now, the problem is when you go to the kitchen, you don't have chicken. So you have to maybe go to the supermarket and get the chicken, really mess up and really go deviate a lot from your plan. And the states are really different one from another. There's another possibility to this, and as we have the same plan, but instead of doing it chicken soup, we change the ingredients, and we do another type of soup that is really similar, that could be some type of turkey that does not change our final goal and is really similar to it, but it's not the same. Now, the difference between plans is way less. In this example, you can see the bottom one, the distance between states is reduced, but not every state is achieved, compared to the top one, which every single state of the plan has been achieved. Now, from this, what we do is we try to get some metrics. So how well is the plan being followed? We get the two main one, which is maximizing the plan state visited and minimizing the plan difference. Maximizing the plan states is the top example, and minimizing is the bottom example I just showed. Now, for this, we put two metrics, the hot metric and the soft metric. The hot metric is a true-false metric, where if the plan state is achieved, you get a 1. If it's not, you get a 0, some sort of that type of metric. Well, the soft metric measures also how the distance between the plans. So for the maximizing, just a simple one, which is the percentage of the plan that has been achieved. Now, ideally, this plan metric, this plan state visited, should be 1. You want to visit all the plan states. While minimizing is how many non-plan state have been achieved, so have been executed with respect to all the executed plan states. Ideally, you want it to be as close to 0 as possible. In the case of the soft metric, it gets a little bit more complex, where we introduce the gamma, which is just a distance metric between 2 states. In it, what we do is we see which is the minimum distance between an executed state and a planned state, and we average up above all the planned states. Same thing we do with the minimizing, but instead what we want is from all the executed states, the minimum distance to the nearest planned state. Now, as we see the minimizing, we want to get as near to 0 as possible, and the maximizing as close to 1. Now, when we do reward functions, we want to maximize. Maximizing a reward function makes us try to rethink a little bit what we want to do. So when looking at reward functions, we can have a sparse reward where we only get the reward once we achieve the final goal, which is what we call at end, the reward at end, or we can have a per step reward, for example, achieving a planned state. So basing on everything on the metric I just showed, what we're going to do is we're going to have an at-end reward and a per-step reward for every metric. The first one, maximizing planned states, is just the same one. While the minimizing, we take this, we subtract it from 1 to try and maximize the reward. For the per-step reward, what we give is, let's give 1 over the amount of planned states every time you achieve a planned state, which will cap the total reward to 1, and otherwise you will not get any reward. Meanwhile, for the minimizing plan difference, what we get is 1 over the distance to the plan, just current state to distance to the minimum distance to the plan. We add the epsilon, so if the distance is 0, this doesn't goes to infinity. So what we're trying to do is basically minimize the distance while maximizing the reward. So now we've established what the reward we're sending to the agent. We need to establish what is the observation are we going to send to the agent. So in this, what we're all basing it all in, and the experiment we're going to run are on a grid world. So from this, what we're going to send is the current state. Now, just to give an explanation, we have the walls and you have this gray circles, which are obstacles inside of the world. And finally, you have the green square, which is the goal state, and your position, which is the blue circle. To this, we add some set of visible plan states. Now, this set of visible plan states is only sent the dynamic part of the state. The dynamic part of the state, we define it as the part of the state that is only actions can change. So for example, in this case, it would be the position. So where the state of the obstacles is not sent to the reinforcement learning agent. Another key fact is, as reinforcement learning has to have fixed observation size, then we need to fix the amount of states that we send to the reinforcement learning agent. To do this, we say, well, this is the amount of visible plan states that the agent can see. This amount has to be greater than the maximum expected block state. When I mean block states, these are states that continuous cannot be achieved. So if, for example, in the grid world, if we had 5 obstacles continuous, then in continuum, then the maximum number of plan states should be, visible plan states should be higher than 5. In our case, the way it's good, we only, in this grid world, the maximum number of block states, it's 4. So we run some experiments in this grid world environment, and we put a number of plan state visible by the agent of 5. We trained on about 10,000 episode and tested on the heart metrics and also on a goal evaluation metric, which gives us a +1 if the final state is achieved, a 0 otherwise. This is just to view how, to give us more information how the agent is behaving. So we run it on 3 different environments that simulate different parts, different problems that could happen. So first is a non-deterministic action outcome. For this, in every type of environment, we have something that the planner sees, which the obstacles there could be preference in the users that we don't want the agent to pass, but when it's in the real world, it doesn't see those. So it needs to follow the plan as near as possible, trying to evade those. Now, what does the non-deterministic action outcomes happen? Well, if we center on the blue circle, we can go right 2 or left down 2, up 2, or left 2. There's a better example if we get in the middle of the grid and we get this orange circle. The orange circle at any moment with a 10% chance, possibility can be moved out of the state to another one. So it doesn't execute the action, it just moves to another state randomly. Now, going back to the visible plan states, the blue circle can only see those 5 states. All the other part of the plan is not visible by the agent. In the case of the orange one, the next ones are those. So then we have unachievable plan states. When we talk about unachievable plan states, as we see, we have the planner and it made a plan with his metrics, with his obstacles and his preferences. But when we execute in the real world, 2 of the states are blocked and you cannot achieve them. Well, the agent is past those plan states as if they could be achieved, but when it sees the current state, it sees that it is not able to do it. And now this is a question that we discuss afterwards, is which is the better way to go with this? So should the agent execute the 2 states that it can and then go to the goal, or just go around the goal? That depends on what is the definition of following a plan. Finally, we also introduced a 3rd one, which is the missing action. As you can see in the planner, we have all the actions, and just highlighted that action, if you go to what the agent sees, is missing. So we have some type of action that if not done, the next action cannot be done. The agent here has to improvise and try to find a way to do it. As before, it doesn't see the action. So the orange circle, when we send in the plan states, we don't send the corner action that is not available that is available for the planner, but not for it. So we got some results, and for the non-deterministic action outcomes, just remember that for gamma P, we want it to be as close as 1 as possible, also for gamma G, but for gamma N, we want it to be as low as possible. What we see is that the maximizing plan visited states outperforms all the others. Now, especially the end one in this case, compared to the minimizing, which once we introduce the distance metric, we see it performs poorly, but both of the 3 agents perform over 75% of the plan. Then here's a small simulation of what the agent does. When we see a black line, it means that the agent has been moved without his intention to be. So it is able to rejoin the plan and keep executing it. As you can see, even if it's moved, it is capable of achieving the plan. Okay, so, sorry. So now the unachievable plan states. Now this is way more complex, as I asked before, because even myself, I had a few discussions with Michael and other colleagues about how do we execute a plan that is blocked? What happens when we block the states, and how do we manage that? So the reinforcement learning agent behaves really poorly in this case. Now, this could be solved with more training, better reward functions, and better hyperparameter tuning, but defining a better reward function should need a better definition of what is flowing in the plan. The best one is the per step reward of maximizing plan states. And as you will see in this short video, 10-second video, what it does, it found out that just going in one direction has the highest probability of achieving a plan state, achieving a maximum plan states. Now, and finally, for missing action, we see that the greatest performance is done by the reward function that is per step and maximizing plan states. Now, the binodal distribution in the end reward of the maximizing plan states is due to the fact that when we run the experiments and saw what was happening, it got lost when the action was missing. So it had a 50% chance of getting lost or executing the plan. In the case of the per step reward, that didn't happen. So just here, a small simulation I just highlighted with a red circle the action that is going to miss. And as you can see, it is capable of taking that action as it needed. Now, as you can see, not always is not the ideal action that the planner saw, but the reinforcement learning agent is capable of substituting that action for another one that would achieve the goal. In this example, it's curious that it really just skips to the goal. And this is because we're given information about the goal, and it is given reward for achieving the goal. Finally, for future work, we have to define a better state distance metric that is domain independent. Currently, right now, the one we're using is just a known vector magnitude, so distance, normal distance. And we also need to create a better estimation for generalizing the maximum block states for all problems. Now, the mapping between a general plan execution metric to domain-specific rewards, this could be some ideas we're currently having is adding some shaping reward that divides the reward into general domain and domain specific, and the domain specific is trained through metagradients. And finally, we applied this with a really simple grid rule domain to show that it is possible, and we think that it is possible to have this reinforcement learning agent that executes plans made by humans with abstractions, but this needs to be proven in other domains. So thank you very much. That was all.
Thank you very much. And so that was brilliant. And I would invite questions from the audience right now. Eris, I can see your hand up. Please go ahead.
Thank you. This is very interesting. Maybe I hang out with machine learning people too much, but my question is this better than just using reinforcement learning to solve the problem directly?
So,
or rather, is it easier to train the agent, right?
So more than easier to train or easier to solve the problem, we're going that currently right now, there's some abstractions that the humans make that are not present in the model or really hard to make in the model. Also, the distrust of the planning people in that make satellite that make plans for satellites do not fully trust that $1 million idea is fully autonomous with reinforcement learning. So what this gives us is a way to first explain why the reinforcement learning is doing the action, that it's basically just following a plan, and is it's better for understanding and getting those abstractions from humans that are not present in the model.
So can you provide any guarantees on what execution will look like using this method?
Yeah, you could try and explain the execution better, not fully guarantee, because as reinforcement learning, it's a black box, and maybe in an environment state that it has never seen, it can act however it likes, but you can try and explain the actions from having a plan, and it's trying to follow the plan.
Okay. Wheeler.
Okay, we have Wheeler with his hands up. Go ahead.
So I guess I'm a search and planning guy. So I love search and planning. So it seems like you're trying to avoid search and planning by doing something else to follow some old obsolete plan. Why can't we just be planning all the time? Why can't we just call the planner again? Like, what's wrong with planning? Why do you not want to do planning? Are you against planning? What is this?
So it's could be really time consuming when you get in really complex environments and really complex decision making. While reinforcement learning is one strain, it is really fast, and really the resources you consume is really low.
We got great planners. Planners are fast. Planners are your friend. You want planners. You want to be calling a planner every millisecond.
Well, from my experience, it's really it's really slow to call a planner.
Must be using the wrong planner.
But Wheeler, there is a point.
I can't convince him.
Wheeler, there is a point on how much does it take. I mean, how frequently can you call a plan? I mean, you know, the warming up period. It depends on the application. So this can be a blocker. This can be a blocker for me. So I think, but of course, we have to be trying. But I think it's important to be aware of these corners. We probably don't use them so frequently.